We finished off our last lecture talking about voltages. Voltage in a circuit is a measure of the potential energy per unit charge at the various points in the circuit. And when we talked about voltage, we talked about two different ways you could measure it. One was the relative voltage between any 2 points in the circuit. For example, the voltage across a resistor or the voltage between 2 other points in the circuit. The other voltage designation, what we call the absolute voltage designation, was the voltage at a point in the circuit referenced to a point in the circuit that we call ground or 0 volts. And then we talked about how you could go from relative voltage to absolute voltage and vice versa. We're going to talk a little bit more about that in this lecture here. We're going to start by defining what we mean by a node and talking about node voltages. So when you have a circuit with different components connected, voltage sources, current sources, resistors, capacitors, etc., the points where these different components connect is called a node. So a node is a point in a circuit where 2 or more circuit elements connect. Technically, if you have 2 wires that are connected together, it is not considered a new node. It turns out that every node in a circuit has an associated absolute voltage associated with it. Let's look at this figure down here. So let's assume this whole area at the bottom, it's just wires, and so we consider it one node, and we're going to call that ground. So we'll give it the ground symbol, and of course say that that is 0 volts. Then this area up here on the left is considered another node. So we can give it an absolute voltage designation. Maybe we'll call that V sub A. This area right here is another distinct area. We can call that node V sub B. And then on the right, this area here is another node. So we call its voltage V sub C. So notice in between here, like all of this wire here is considered one node. Even if you drew another circle here, that does not make that a separate node. That is all one node because it's connected just by wire. Likewise on the bottom here, all of these joints here, because they're just connected by wire, not by other components, are considered the same node. The reason we do that is because the wire itself does not give rise to a change in voltage. Now, technically, the voltage along a wire will not necessarily be completely constant because of things like magnetic fields, etc. However, we're going to be ignoring that in this class. So every point along these wires on the bottom here, we're going to call the same voltage 0 volts. So the first thing you see when you have a circuit this way is you can simplify how it's drawn by collapsing the nodes. For example, all of these points on the bottom, even though it looks like they're separate nodes, it's really one node. So you can draw it as one dot there. Likewise, we have a node there, and a node here. And so between here, you have the voltage source, and there's a capacitor. Then between this node here and this node, you have your switch. Between these nodes, you have, that's an inductor. Between here, you have a diode. And between this right node and the bottom node, you have a capacitor and a resistor. So this is a simplified version of the same exact circuit. And then down here, we'll call this ground or 0 volts. And what we see is every 2-terminal circuit element, so every circuit element always connects exactly 2 nodes. So that circuit element connects those nodes. This circuit element is between those nodes, etc. And so that means that the relative voltage, or the voltage across any circuit element, can always be written as a difference between 2 node voltages. For example, suppose you were interested in the voltage across this inductor. Let's call it V1. You could say that V1 is equal to the voltage at this node, which is VB, minus the voltage at this node, which is VC. So once again, you could say that for every single circuit element, the relative voltage across that circuit element, you could always designate as the difference between two node voltages. So let's use some of the things we learned about voltages and nodes and the difference between absolute and relative voltages to solve this problem here. So here we're given a circuit with 4 different elements. We don't really care what these elements are. At this point, they're just blue ovals. But we're told that there are going to be 4 nodes, A, B, C, and D, and node D is connected to ground, so we're going to say that that is 0 volts. And we're told a couple things. We're told that the relative voltage between nodes A and B is 2 volts. So in other words, we're saying that this point on the left is 2 volts higher than this point on the right. Likewise, we see that VBC is negative 3 volts. That means that point B is negative 3 volts higher than C, or the point C is 3 volts higher than B. So you have a 3 volt difference there, and notice the plus there. Now we could have written it this way if we wanted to. Rather than putting 3 volts with the plus on the bottom, we could put the plus on the top and the minus on the bottom and written it as minus 3 volts. These two designations are absolutely identical, although it probably makes more sense to use the designation in blue. We're also told that VCD is 6 volts. That means that this voltage is 6 volts higher than that voltage. We have something like that. And then, of course, VD equals 0 volts. So that's given because this is ground. So now we're asked to find the following absolute and relative voltages given that information that we have already. And then we're asked to determine how much energy is absorbed or released by a 2 coulomb charge that moves from point A to point D. So the first thing we're asked is, what is the absolute voltage at point B? Well, what we know that the relative voltage VBC is equal to VB minus VC. Therefore, VB is equal to VC plus VBC. VC is given right here. Actually, it's written as VCD, but VCD of 6 volts is the same thing as saying VC is equal to 6 volts. Why? Because it's relative to D, which is ground. So VC of 6 volts is an absolute voltage. VCD of 6 volts is a relative voltage, but they happen to be the same thing. So VB is VC, which is 6 volts, plus VBC, which is given, minus 3 volts. So we get 3 volts. So the absolute voltage at point B is 3 volts. Next thing we're asked is to find the relative voltage VAD. Once again, the relative voltage VAD is the same as the absolute voltage VA. Why? Because D is ground. We also know that the relative voltage VAB is equal to VA minus VB. Once again, a relative voltage is always the difference between two absolute voltages. So that means that VAD, which is the same as VA, can be written as VB plus VAB. VB, we just solved for, it's 3 volts. VAB, we were given up here, 2 volts. So we know the absolute voltage at point A is 5 volts. Finally, we're asked to find the relative voltage between nodes C and A. Now here, notice this is not the voltage across one element. We're talking about the voltage of this point with respect to that point. So there's not a single element connecting these two. Nevertheless, there is still a relative voltage between C and A. So in other words, to have a relative voltage, the two nodes do not need to be connected by one element. In this case, there are a couple different elements. But the relative voltage of C with respect to A is the same as the voltage at C minus the voltage at A. So once again, the relative voltage is the difference between two absolute voltages. VC, we were given in the problem, 6 volts. VA, we just solved for in the step above. So we get 6 volts minus 5 volts. We get 1 volt. So what we see so far in this problem is given a couple relative or absolute voltages, you can find the rest of them sometimes just by looking at the relationship between relative and absolute voltages. Okay, second part of this question now says, determine how much energy is either absorbed or released by a 2 coulomb charge that moves from A to D. So suppose we have 2 coulombs of charge at point A and it moves to point D. It does not matter whether it goes this direction or this direction. All that matters is the difference in voltage. Sort of like if you have a rock on top of a hill and you're asking how much energy that rock gains or loses if it goes to the bottom of the hill. It doesn't matter how it gets down to the bottom of the hill, it loses potential energy, which is absorbed by something else. So in this case, the energy absorbed or released is the voltage difference. So it's a 5 volt difference going from A to D. So 5 volts times the charge, which is 2 coulombs. So you get 10 joules. Now the question is the energy absorbed by the charge or is the energy released by the charge? Well, the charge is going from higher to lower voltage, so it goes in the direction it wants to go. That means that it is losing energy. So you get 10 joules is released by the charge, which also means that 10 joules are being absorbed by the circuit. In other words, when that charge moves from point A to point D, regardless of how it got there, it is doing work. It is doing work. It is maybe moving a motor, maybe vibrating a speaker, maybe lighting a light. But the bottom line, when a charge moves from a higher to lower voltage, it is releasing energy into the circuit. So let's talk about this energy that's being released by talking about power and energy. So if you think about when a charge moves through a circuit element with a voltage drop across it, the energy is going to be either absorbed or released by the charge and then being released or absorbed by the circuit. If this charge absorbs energy, the circuit releases energy and vice versa. So when you have a charge moving through a circuit element, you get energy is absorbed or released by the charge, which then means that the energy is released or absorbed by the circuit. Power, as you might remember from your first physics course, is the rate at which work is done or the rate at which energy is absorbed or released. So power is energy over time. Power has the abbreviation P, once again, capital P meaning a constant power, lowercase p meaning a power that varies with time. Unit of power, as you remember, is a watt. So 1 watt is 1 joule per second. Energy over time, 1 joule per second. Now let's think of how that relates to voltages and currents. Voltage is energy per unit charge. Current is charge per unit time. So if you multiply voltage times current, basically these charges cancel each other out and you get energy per unit time or power. And this gives us an important relationship between voltage and current in a circuit. The power released or absorbed by a circuit element in an electrical circuit is equal to the voltage across the element times the current through the element. P of T is V of T times I of T. What's really important, and we're going to talk about this in the next couple slides, is the orientation of the voltage and the current. Remember, with the voltage, you not only have a magnitude, you also have to have a plus and a minus. So you have the polarity. Likewise, with the current, you not only have a current, but you need a direction. Anyway, for this equation to make sense, the current arrow has to go from the positive to the negative terminal. We call that the passive sign convention. We'll look at that shortly. So 1 watt of power corresponds to the flow of 1 ampere of current through a 1 voltage drop in voltage. 1 watt is 1 volt ampere. Another important result is conservation of power. So in a circuit, you're going to have these different circuit elements. Some will be absorbing power, some will be releasing power. Anyway, the sum of the powers has to be 0. We call that the conservation of power, also called Telegin's theorem. And we'll see in some examples how this is a very, very important result. Another way you can look at this if you want is you can say that the sum of the power absorbed by some circuit elements is equal to the sum of the power supplied or released by other circuit elements. So let's talk a little bit more about this sign convention here. We call this the passive sign convention. So when evaluating the power equation, power is voltage times current, first thing that we note is that a positive power means the power is being absorbed by the element. So if the power associated with an element, a resistor, a capacitor, or whatever, is positive, it means that element is absorbing power. The next important point is that for this equation to work properly, as I said in the previous page, the current you have to be using is the current into the plus terminal. So if the voltage is given like that, the current you want to use is that current, not that current. If an element is delivering power, that power is being delivered to a charge to move a charge to a higher voltage. If an element is absorbing power, what is happening to that power? Well, it could be dissipated as heat. For example, when a resistor absorbs power, it heats up a little bit. We call that Joule heating. It could be stored temporarily in an electric or magnetic field. For example, that's what happens with capacitors and inductors. They temporarily store this energy in either an electric field or a magnetic field. Or the power could be converted to either a chemical form or a mechanical form. For example, a motor converts the energy to a mechanical form. A speaker converts it to a mechanical form by vibrating. A chemical form when you're charging a battery. So normally a battery is going to deliver power, but you could have a battery absorbing power. When it's absorbing power, basically the energy is being absorbed by the battery in a chemical form so that it can be used later on to deliver power. So the equation for power, voltage times current, seems very simple. However, it's a little confusing because of the signs and the sign convention. You have to be very careful when using the power equation to make sure that you get the signs correctly. So we have 4 examples here to show how it's really important and very easy sometimes to get it mixed up. So we're asked to find the power absorbed or supplied by each of these 2 terminal elements shown below. So we have these blue blobs. We don't know what they are. Are they resistors, voltage sources, capacitors, speakers, motors? It really doesn't matter. But for each one, we know the voltage and the current associated with that element, and from that we can determine the power. So this first one is pretty straightforward. We see that there's 3 volts across it, so the top node is 3 volts higher than the bottom node. And we see that we have 2 amps going into the top node. So this is following the passive sign convention on the previous page. Passive sign convention says that the current, when using the power equation, the current has to be the current going into the plus terminal. So here, the power absorbed is 3 volts times 2 amps or 6 watts. Fairly simple. These other 3 examples, however, are going to get a little more difficult. Second example, we still have 3 volts and 2 amps. However, if you look now, this minus sign is at the top. And so this does not follow the passive sign convention. So what we could do if we wanted to is we could redraw this circuit as minus 3 volts with the plus on top. So notice 3 volts with the plus on the bottom is the same as negative 3 volts with the plus on top. Now, the power absorbed is what? It's minus 3 volts times 2 amps, or minus 6 watts, which is saying that this thing supplies 6 watts of power. If you look at the circuit on the bottom left, here the current arrow is going into the plus terminal, so we're fine. So the power absorbed is what? It's minus 3 volts times minus 2 amps, or 6 watts. So once again, this element is absorbing 6 watts of power. If we wanted to, you could have redrawn the minus 3 volts with the plus on top as 3 volts with the plus on the bottom. The minus 2 amps going into the plus terminal, you could rewrite as 2 amps plus 2 amps going into the bottom terminal. It's the same thing. Notice we're still obeying the passive sign convention. This arrow is going into the plus terminal, so we get 2 amps times 3 volts, or 6 watts. Last example, we now have minus 3 volts with the minus on top and the plus on bottom, and we have 2 amps coming out of the top terminal. So once again, if we want to make sure we satisfy the passive sign convention, let's rewrite things. Minus 3 volts with the plus on bottom is the same as saying 3 volts with the plus on top. 2 amps going to the left is the same as minus 2 amps going to the right. So now we have the arrow entering the plus terminal, so we could use the power equation, and the absorbed power is 3 volts times negative 2 amps, or negative 6 watts, which is once again saying that this element is supplying 6 watts of power. So what we see in these examples is that although the math is simple, it's just a voltage times a current, you do need to be very careful about the sign convention. Once again, when you have an element and you have a voltage across it, if you have your voltage designation with the plus somewhere and the minus somewhere, regardless of what this number is, regardless of whether that number itself is positive or negative, to use the power equation, the current arrow has to be going into the terminal that is called the plus terminal. Once again, it doesn't matter what the magnitude of this current is, the arrow has to be going that way. And if you have a situation such as here or here, where the passive sign convention is not upheld, you need to move things around in order to get the power equation to work correctly. This example is going to illustrate the conservation of power. At the same time, we're going to look again at the power equation for determining whether the power associated with each element is positive or absorbed, or negative, meaning supplied. So we want to find the power absorbed or supplied by each element and then show that the conservation of power is upheld. Okay, so let's look at these element by element. So first element here, we have 12 volts across it. And then the current into the plus terminal would be the current in this direction. The current into the plus terminal, since we have 2 amps leaving that terminal, you have negative 2 amps entering the terminal, or minus 24 watts. So element 1 is actually supplying power. Component 2, you have 2 volts across it. The plus terminal is on the left, and we have 2 amps going from plus to the minus terminal, so we don't have to do any sign changes there. So this one absorbs 4 watts. The third element, we have 4 volts across it. The current is going down in that direction, so it's entering the plus terminal. So we have 3 amps entering the plus terminal. 4 volts times 3 amps, 12 watts. The fourth element, there's 6 volts across it. And once again, we have 3 amps hitting the plus terminal first. So that absorbs 18 watts. Fifth element, up here, you have 7 volts across it. The current into the plus terminal is a current in this direction. But we have 1 amp going from right to left, which means we have to have minus 1 amp going left to right. So that's minus 7 watts. P6, you have 3 volts. The current entering the plus terminal is that current, which is the same as that current, 1 amp. We get 3 watts. Finally, P7, 3 volts across it, times which current? Not this current, because that's a current leaving the plus terminal. The current we need is the current entering the plus terminal, which is minus 2 amps, or minus 6 watts. So if we look at this, P1, P5, and P7 all supply power. P2, P3, P4, and P6 all absorb power. So element 1, 5, and 7 provide power to the charges flowing through the circuit. The charges flowing through the circuit then give power to elements 2, 3, 4, and 6. And sure enough, the supplied power, if you add up those numbers, 24 plus 7 plus 6, 37 watts are supplied, and the absorbed power is 4 plus 12 plus 18 plus 3 is 37 watts. We get conservation of power. In fact, suppose we didn't know one of these values. Suppose you did not know the power supplied or absorbed by, let's say, element 4. You can actually solve the circuit knowing everything else. For example, if you did not know that that was 6 volts across there, you would still know from conservation of power that element 4 would have to absorb 18 watts to get everything to add up to 0. If it had 3 amps going in it and it absorbed 18 watts, you would know that it would have to have 6 volts across it with the plus on top there. So how does this relate to energy? So power is the rate of energy flow. So energy then is the time integral of power, or power is the derivative of energy. So P of t is dW of t dt, and the energy is a definite integral. W of t is W of some starting point t naught plus the integral of from t naught to t of P of tau d tau. Just like with the charge current relationship, we use a dummy variable tau here so that we don't get confused with this t that's in the integral. And the energy starting from minus infinity would be the integral from minus infinity to t of P of tau d tau. So let's look at a problem here. So here we have a circuit element. We do not know what the circuit element is, but we have a graph of the current through the element, and we have a graph of the voltage across the element. And we're asked to sketch the instantaneous power and energy for the element. So we can do it both graphically and mathematically, or analytically as we call it. So looking at it graphically, the instantaneous power, the power at any time, is the voltage across the element at that time times the current through the element at that time. We need to make sure, by the way, that we're using the passive sign convention. Once again, our plus terminal is up there, and the current arrow is entering the plus terminal, so the passive sign convention is upheld. One thing I want to point out, just because this plus terminal is up here, it does not mean that the voltage up here is always higher than the voltage down here. For example, in this time period here, the voltage is negative 10 volts. So between 10 and 30 seconds, the bottom terminal actually has a higher voltage than the top terminal. So just the fact that it has the plus symbol next to it does not mean it is the higher voltage. That's just a polarity. It's not necessarily indicating that that voltage is higher. Anyway, to find the power, you basically point by point multiply the current, the blue line, by the voltage, which is the green line. See what we get. So first off, for time less than 0, because current and voltage are both 0, your power is going to be 0. Now, between 0 and 10 seconds, the voltage is constant, 20 volts, and the current increases linearly from 0 up to 2. So by the time you get to 10 seconds, you get 2 times 20, or 40 watts. So the power is going to rise like that. What happens at 10 seconds? The current is still 2 amps, but now the voltage all of a sudden jumps to negative 10 volts. 2 times minus 10 is negative 20. So the power is immediately going to jump down from plus 40 watts to minus 20 watts. And then between 10 and 30 seconds, the voltage once again is constant, now negative 10 volts, and the current starts decreasing linearly. And by the time you get to 30 seconds, it should be 0 again. So this is the power. So what we see here is this element is absorbing power between 0 and 10 seconds, and it's delivering or supplying power between 10 and 30 seconds. The energy is just the integral of the power. We saw that from the equations on the previous page. So it's basically just the area under the power curve. So if you think about this now, as we start integrating the area, it's going to start small at first and get more and more and more and more and more area up to 10 seconds. And then starting at 10 seconds, the area is going to decrease quickly at first and then more slowly. So what we're going to see, without actually doing the math, we're going to see that the energy is going to look like a parabola. It's going to start at 0, then it's going to parabolically increase. So the value at 10 seconds, you have to look at the area inside this triangle. So a triangle has a height of 40, a width of 10. 40 times 10 is 400, divided by 2. You said the area is 200. So the value at 10 seconds is 200 joules. It's going to start decreasing now at 10 seconds. It's going to decrease quickly at first because there's a lot of area at first, and then the added area gets less and less. And if you look at the total area of this triangle, once again, it has a height of minus 20 and a width of 20. So you get negative 400 divided by 2, we get an area of minus 200. Why is it a negative area? Because it is below the x-axis. So what we see is by the time we get up to 30 seconds, it just so happens in this example that we're going to get back down to 0 again. And it's going to decrease like a parabola. We're going to redo this problem on the next page, but we'll do it with equations instead, and we'll actually get equations for this parabola here and this parabola here. So at this point we did it just graphically, but now let's look at it more formally with math equations. So analytically, the first thing we want to do is find expressions for these currents. So the equation for this, using the slope-intercept form, it intersects the axis at 0 and has a slope of 0.2. So that's 0.2t. This line segment here, let's extrapolate up to there, that has a y-intercept of 3. So this line segment is going to be 3, and the slope is negative 0.1, so it's 3 minus 0.1 t. So I of t, if you wanted to get a mathematical expression for it, it's going to be 0 for t less than 0. It's going to be 0.2 t amps. That's between 0 and 10 seconds. It's going to be 3 minus 0.1 t amps. That is between 10 and 30 seconds. And once again, it's going to be 0 amps again for t greater than 30 seconds. The voltage, a little simpler. V of t mathematically is going to be 0 volts for t less than 0. It's a constant 20 volts for t between 0 10 seconds. It's going to be negative 10 volts between 10 and 30 seconds, and once again 0 volts again for t greater than 30 seconds. Power is just the voltage expression times the current expression, once again making sure that we're obeying the passive sign convention, which we are. So the power, 0 watts before 0. Then we're multiplying 0.2t times 20, or 4t watts between 0 and 10 seconds. Between 10 and 30 seconds, we get 3 minus 0.1t times minus 10, or we get t minus 30 watts between 10 and 30 seconds. And finally, for t greater than 30 seconds, we get 0 watts again because both the voltage and the current are 0. One other thing I should point out here, I've been a little sloppy with my less than or equals here. Technically these should probably all just be less thans, not less than and equals, because we do have undefined situations at some of these points here. So I just want to point out I was a little sloppy with my designations there. So the power we can draw once again, it's the same thing as before. We see it's going to be 0, then it's going to be 4t between 0 and 10 seconds. It's going to be t minus 30 between 10 and 30 seconds. And it's going to be 0 again for t greater than 30 seconds. So now we want to find the energy. Power, once again, we'll redraw from the previous page. That was 4t. That was t minus 30. It's 30 seconds. That's 10 seconds. Now, what is energy? T less than 0, the energy is 0. Okay, how about between 0 and 10 seconds? So for time, between 0 and 10 seconds, what do we get? We get the energy is the energy at time 0 plus the integral from 0 to t of p of tau d tau. The energy at time 0 was 0, so 0 plus the integral from 0 to t. P of t is 4t, so p of tau is 4 tau d tau. And notice, once again, we're using this dummy variable tau. When you integrate 4 tau, the integral of 4 tau is 4 tau squared over 2. You evaluate that at the upper limit of the integration, and then subtract from that the evaluation at the lower limit. So we get 4t squared over 2 minus 0, or 2t squared joules, which is going to be a parabola. And when t is 10, we get 200. So notice this agrees with what we figured out just from looking at geometric arguments earlier. Now, for t between 10 and 30 seconds, what do we get? The energy is the energy at time 10 plus the integral from 10 to t of tau minus 30 d tau. The value at 10, 2t squared, plugging in t equals 10, we get 200. We get 200 plus the integral of tau minus 30 is tau squared over 2 minus 30 tau. And this expression gets evaluated at the upper limit of t and the lower limit of 10. So we get 200 plus t squared over 2 minus 30 times t minus 10 squared over 2 minus 30 times 10. And once again, we see why it's so important to use this dummy variable, because you have this tau in here, and then you also have this t in here. So once again, using the dummy variable rather than using t for the whole problem makes it much more clear what you're supposed to be doing. Anyway, you work out this math, you get 200 plus t squared over 2 minus 30t minus 50 plus 300. Finally, we can clean up the math here to get t squared over 2 minus 30t plus 450. The units are joules. You plot that on the plot here, you get the rest of this parabola, which once again agrees with what we had on the previous page. Finally, if you wanted to check this math here to make sure that this was correct here and here, evaluate these functions at 0, 10, and 30. For example, this thing evaluated at 0, you get 0. At 10, you get 200. This function, you evaluated at 10, you get 200. You evaluated at 30, you get 0. So once again, this sort of shows that your math is correct. Anyway, this concludes the discussion of power and energy, at least for now. We will revisit this many times throughout the semester. Next class, we will start talking about basic circuit elements. Have a good day.